we're going to look at some examples from section 2.6 and 2.7. Okay, and first, section 2.6, solving other types of equations. Okay, so one type is to solve equations with radicals or ones with rational exponents. So if we want to solve an equation that has a radical, and it's in this form, the nth root of x is equal to c, you can raise both sides to the nth power. Okay, so for example, if we want to solve the cube root of 2x minus 3 is equal to 3, we'll raise both sides to the third power. Okay, and we get 2x minus 3 is equal to 3 cubed, which is 27. And now we have a nice linear equation. So we'll add 3 to each side. We get 2x is equal to 30, and then divide by 2. Okay, so x is just 15. On the other hand, if we have an equation in this form, x to the m over n is equal to c, some constant, we're going to raise both sides to the reciprocal, or the n over mth power. So if we want to solve x minus 1 to the 2/3 is equal to 25, we'll raise each side of the equation to the 3/2. Okay, and our properties of exponents say when we raise a power to a power, we multiply them together. And so we multiply 2/3 by 3/2 and just get 1. So all of a sudden, the left-hand side is just x minus 1, and the right-hand side is 25 to the 3/2. Okay, so if you recall, when we have some number to a rational exponent, so x to the a over b, we can rewrite that as the bth root of x to the a, and you can write the a in one of two places. So it could be under the radical or outside. Okay, so in this case, we're going to take the square root of 25 and then cube it. So that's 5 cubed, or 125. At the same time, we have to recognize that we just took the square root of both sides in an equation. And I can't forget that there are two solutions to this problem. So put plus or minus 125, and now add 1 to both sides. And we get x equals 1 plus or minus 125. Or, so 1 plus 125 is 126. 1 minus 125 is negative 124. And check your solutions in the initial equation. If we want to solve an absolute value equation of the form absolute value of x is equal to some constant c, where c is greater than or equal to 0, we end up with x equals plus or minus c. Let's look at this example. If we want to find absolute value of 5, for instance, that's 5, and the absolute value of negative 5 is also 5. So if I wanted to solve the equation absolute value of x equals 5, I know that x could be one of these two things. It could be negative 5 or 5 because the result, once we took the absolute value, was positive 5. So x is plus or minus 5. Okay, using that same idea, I want to isolate the absolute value in this example. So we'll subtract 3 from each side of the equation. We get absolute value of 2x minus 4 is equal to 2. And now we'll take this inside expression, 2x minus 4, and set it equal to plus or minus that constant, so plus or minus 2. Okay, add 4 to each side. and we get 2x is equal to 4 plus or minus 2, and then divide by 2. Okay, so altogether, x equals 4 plus or minus 2 over 2. This produces two answers, and so first we'll take this as a plus. 4 plus 2 over 2 is 6 over 2, or 3. 4 minus 2 over 2 is 2 over 2, or 1. So x could equal 1 or 3. Now, if, for instance, I had an equation that looks like this, absolute value of x is equal to negative 4, I notice, anytime I take the absolute value of any number, the result is always greater than or equal to 0. And so this will never happen, and so we'll say no solution. Well, sometimes we want to solve equations that don't look like quadratic equations initially, but could be solved using a quadratic equation. And so this first one, example 1, is a rational equation. 6 plus 10 over y squared is equal to negative 19 over y. We want to try to eliminate the fractions, if possible. So we'll multiply both sides of this equation by the least common multiple of the denominators. In this case, it's going to be y squared. Okay, and distribute, and so we have 6 times y squared is 6y squared, and 10 over y squared times y squared is 10, and then on the right, one of the y's will cancel, but there's still a y, and negative 19 times y is negative 19y. We'll move all terms to one side and try to factor or use quadratic formula. And so we have 6y squared plus 19y plus 10 is equal to 0. Okay, so I'll try to factor. We can use combinations like 6y and y, because the product should be 6y squared, or 3y and 2y. These other terms, the last ones, their product should be 10. So we can use 1 and 10 or 2 and 5, and in the reverse order if needed. Okay, so after a little bit of work, I realized that this should be 3y and 2y, and then I'm going to try a 2 and a 5. And how I test it out is just to do this combination of the sum of the product of the outer and inner terms. And so that's 3y times 5, or 15y, and then plus 2 times 2y, so plus 4y, which is 19y, that middle term. Okay, now set each factor equal to 0. So 3y plus 2 equals 0, or 2y plus 5 equals 0. And solve for y. Okay, so if we subtract 2 from each side of the first equation, we get 3y is equal to negative 2, and then divide by 3, and y is equal to negative 2/3. Okay, so for the second equation, we would subtract 5 and get 2y equals negative 5, and then divide by 2. So y is negative 5/2. And performing a quick check on my calculator, I just substitute one of the answers in to each side of the initial equation, and we see that they would each result in a 28.5, and so I know the first answer works. Do the same for the second, and hopefully you'll see that it works as well. Okay, well, this next equation really is a quadratic equation initially, and so one option is to just go ahead and expand this left-hand side. Another option is to recognize that the bases of these powers are the same, 4x minus 3, and the exponents are related to one another. The first exponent is twice the second. Okay, so if that happens, we're going to solve this using substitution. So we're going to let, we'll say a equal the base, 4x minus 3. So wherever there was a 4x minus 3, we're going to replace it with a. And we get 4a squared plus 7a minus 15 is equal to 0. Now, again, this is a quadratic equation. We have some different options for solving an equation like this. I'm going to try to factor. If you want to use quadratic formula, that will work as well. So I'll try a 4a and an a, and then a 5 and a 3. And because this product 5 times 3, it really should be a negative 15. I need a negative in one of these blanks. So I'll try a negative 5 and a positive 3. And then double check the outer and inner combination. So 4a times 3 is 12a. And then plus negative 5 times a, which is negative 5a. And that gives us 7a. So set each of these factors equal to 0. And solve. So a is equal to 5/4 for the first equation, or a is negative 3 for the second. Okay. Well, now I recognize that my goal is really to solve for x, not for a. And so let's substitute the expression back in. So we're going to put 4x minus 3 in this spot, and then solve for x. Okay, so for the first equation, we'll add 3 to both sides, and we get 4x equals 5/4 plus 3 is 5/4 plus 12/4 or 17/4. And then divide both sides by 4. And that gives us x equals 17/16. You really are going to multiply those 4's together. 17/16. And then the other equation, we'll add 3 to both sides. And negative 3 plus 3 is 0, so we get 4x is 0, and then divide by 4. And we also get a 0. Okay, so altogether, x could be either of these answers, 0 or 17/16. And sometimes we want to solve higher degree equations. And there's a technique that we could have used to help us factor those quadratics in the last couple of examples. And so let's go over that really quickly. Let's say I wanted to factor this one, 6y squared plus 19y plus 10. And I want kind of a more outlined or concrete approach. And so what I'm going to do is first multiply a by c, or 6 by 10. So I'm going to get a 60, and I'm going to find factors of 60 that add to give me 19. And so I think 15 and 4 will work. And so we're going to replace 19y with 2 new terms that will add to give us 19y. Okay, so 6y squared plus, we'll use the 15 first, but it doesn't matter. 15y plus 4y, and then bring down the 10. Okay, split this grouping down the middle. So group 2 at a time, and factor out the greatest common factor from each pair. And so this first pair, these two terms have a 3 as the common factor and a y. And then I get 6y squared divided by 3y is 2y, and 15y divided by 3y is 5. Okay, bring that sign down, the next sign down, and do the same thing for 4y and 10. So 2 goes into each of those terms, and when we divide both of them by 2, we get 2y plus 5. And now we recognize that we have another common factor but in this expression, which is 2y plus 5. And so we factor that out. And what's left is this other stuff, so 3y plus 2. Okay, so hopefully that is what we found earlier, just a different way. But I'm going to use the same idea, which is called factoring by grouping, for this cubic equation. Okay, so split down the middle, and we're going to try to find the greatest common factor of the first two terms. And so 2 goes into each of them, and an x squared. And divide both terms by 2x squared, and we get x plus 2. Bring that sign down, so this will be a minus. And then 18 and 36, or 18x and 36, have an 18 in common. Really, I'm going to pull out a negative 18. And so negative 18x divided by negative 18 is x, and negative 36 divided by negative 18 is positive 2. Okay, and now we notice again that we have this common factor. And so factor it out, x plus 2, and whatever's left, 2x squared minus 18, is going to go in another binomial. Okay, now you can set each of these factors equal to 0 and continue solving. So either x plus 2 is 0, or 2x squared minus 18 is 0. And that first answer is not hard to find. X is negative 2. The second answer, we still have a quadratic here, and so one option is just to isolate x squared. And so we would get 2x squared is equal to 18, and x squared is 9, and then take the square root of each side. Okay, so altogether, x is plus or minus 3. Okay, so our three answers are x equals negative 3, negative 2, and positive 3. In section 2.7, we're solving linear and absolute value inequalities. And so inequalities have an inequality symbol in them. So greater than, less than, greater than or equal to, less than or equal to. And so we're going to try to first find an inequality that would represent the given statement. So a number is at least 5. We can say x for the number is greater than or equal to 5. I also want to graph this on the number line, and so shade in any of the numbers that will work and satisfy this inequality. So I shade numbers that are greater than 5. But 5 also would work, so I'm going to shade in 5. And then lastly, I want to write our answer in interval notation. So I read my shaded number line just from left to right. So the first number that has been shaded in is a 5. My last number that's been shaded in, the number line is going to go on forever, so to positive infinity. I'll always put parentheses at infinity. And 5, I have a choice. I either put a bracket or parentheses. But if the 5 is included in your answer set, put a bracket. Okay, next, a number is no more than 3. So a number is less than or equal to 3. Okay, and I shade on the number line this time to the left of 3. And I also shade 3 in. And I write this interval, reading the number line from left to right, as negative infinity to 3, and then again with a bracket. Next, a number is between 3 and 5 inclusive. So x is between 3 and 5, and inclusive means to include. So put equals under each of the inequality symbols. Okay, so on our graph, I draw 3 and a 5 in order, and I shade in between them with the 3 and the 5 shaded as well. And so that must mean our interval notation would be bracket 3, comma 5, and then another bracket. Okay, and a number is less than 3 or more than 5. So x is less than 3 or x is greater than 5. So I draw a 3, a 5, and I'm going to shade these just in the correct directions. So less than 3 means shaded to the left of 3 and not shading 3 in. Greater than 5 is to the right of 5 and not shading 5 in. Okay, so this answer is first going to be from negative infinity to 3, and then put parentheses at the end because 3 was not shaded in. And then because I have 2 intervals for my answer, we're going to bring them together with a union symbol, which looks like a capital U. And then start over again at 5, and then go to infinity. So we want to solve linear inequalities, and for the most part, properties of equality will work for solving inequalities. And so we're just going to start by doing whatever we would normally do to solve an equation. So I would distribute, and we get negative 6x minus 8 plus 5 is less than or equal to 2x minus 1. Then I would combine like terms. Okay, so that gives us negative 6x minus 3 is less than or equal to 2x minus 1. Okay, we want to move the x terms together and the constants together. Okay, so I'm going to move this 2x to the left, so I'll subtract 2x from each side, and then at the same time I'm going to move this minus 3 to the right, so I'll add 3. And we get negative 8x is less than or equal to 2. Okay, almost done. Divide both sides by negative 8. Okay, well here is kind of the difference in solving an inequality versus equation. So if you notice the relationship between 3 and 2, for instance, 3 is greater than 2, but if I all of a sudden were to multiply both sides by a negative 1, we get negative 3 compared with negative 2, that negative 3 is the smaller one. So we would have to flip this inequality symbol. So anytime you multiply or divide by a negative when working an inequality, don't forget to flip the inequality symbol. And so we get x is greater than or equal to negative 1/4. Okay, and then if it helps, draw a number line, a shade appropriately based on that inequality, and then write your answer in interval notation. So in this case, it'll be bracket, -1/4, comma, infinity, parentheses. Okay, so this next example, number 2, is a compound inequality, more specifically a conjunction, because it's all written together. But we can solve it all together if you would like. So the first thing I would do is to add 5 to each part. Okay, and we get 2 is less than 1/2 x is less than or equal to 9. Okay, now we want to get rid of the 1/2, so we can divide every part by 1/2, but really that's the same thing as multiplying by 2, so I'll just say times 2 and simplify. So 4 is less than x is less than or equal to 18. Okay, so I'm going to shade between the 4 and the 18 on the number line. Don't shade in the 4, but shade in the 18, and then in interval notation, that'll be parentheses 4, comma 18, and then a bracket. Okay, one of your homework examples looks like this. Use the formula F equals 9/5 C plus 32 to find the corresponding temperature range in degrees Celsius. Assume inclusion. So in part A, it says we are given the temperatures from 5 to 41 degrees. Okay, so we'll say that F is between 5 and 41 degrees, and it says assume inclusion, so we're going to include the 5 and the 41. Okay, but we also have a formula for calculating F based on knowing the Celsius temperature. And so we're going to replace F with 9/5 C plus 32. And we get 5 is less than or equal to 9/5 C plus 32 is less than or equal to 41. And try to isolate C. So subtract 32. Okay, we get -27 is less than or equal to 9/5 C is less than or equal to 9. And then to get rid of the 9/5 kind of quickly, I'll just multiply by its reciprocal. So 5/9. And simplify. Okay, so right now we have C isolated. 5/9 times -27 is -15. And then 5/9 times 9 is just 5. And so we get that C is between -15 and 5, inclusive. Now, in interval notation, that'll be bracket, -15, comma 5. Okay, and try this other part in a similar way and see if you come up with the interval from -40 to -35. Okay, so and one more thing that we want to discuss is how to solve an absolute value inequality. Okay, so for a greater than 0, if the absolute value of x is less than -a, and so that would be the absolute value of x is less than, say, -2, that we know that the absolute value of a number cannot be negative. It's always greater than or equal to 0. And so this will never happen, and we'd say no solution. However, if we had the absolute value of x is greater than a negative number like this, greater than -2, that will always happen because the absolute value of x is always greater than or equal to 0. So this has an infinite number of solutions. I'll just say all real numbers. Okay, now if we instead see absolute value of x is less than a number like 5, is less than 5, then I can kind of fill in some numbers that will work to satisfy this inequality. Now, if you take the absolute value of 6, for instance, that's 6, and 6 is not less than 5. So the numbers over here do not work. 5 does not work because absolute value of 5 is 5, and 5 is not less than 5. But say 4.9, that will work. 0 works. Negative 3, for instance, the absolute value of negative 3 is 3, and 3 is less than 5. But all of a sudden, when I get to numbers over here, like negative 6, absolute value of negative 6 is 6, and 6 is not less than 5, so those don't work. So what we end up doing is shading between negative 5 and 5. Any of those will satisfy this inequality. And so we get x is between negative 5 and 5 for our solution, or parentheses negative 5 to 5 in interval notation. On the other hand, if we have the absolute value of x is greater than 5, we want to just decide which numbers will work looking at a number line. And so if I choose a number like 6, this time it will work. And so I'm going to shade these numbers on the right, but 5 doesn't work. 0 doesn't work. Any numbers between negative 5 and 5 don't work. But once you kind of get down here to the left side, negative 6, absolute value of negative 6 is 6. And 6 is greater than 5. And so all of a sudden, these numbers do work. Okay, negative 5 doesn't work. 5 doesn't work. And so we end up with 2 separate inequality statements. This disjunction is what it's called, that x could be greater than 5, that's the right-hand side, or x could be less than negative 5, that's the left-hand side. But typically when we write them in interval notation, we're going to put the 1 with the negative first, and so that's negative infinity to negative 5 union 5 to infinity. So an example, if I have the absolute value of 2x minus 3 is less than or equal to 9. Okay, I recognize which one of those properties it resembles. And okay, to me it looks like the second one. So what we're going to do is rewrite this as a conjunction. This x is between some different numbers. So in this case, we take out the 2x minus 3. We're going to say 2x minus 3 is between, and then you take the 9 and you're going to put it kind of in two places. You're going to say 9, just like it is on the right, but its opposite is on the left. Okay, and don't forget the equals because it was in the initial inequality. Okay, and then this is an inequality that we know how to solve. So I would add 3, and I get negative 6 is less than or equal to 2x is less than or equal to 12, and divide by 2. Or negative 3 is less than or equal to x is less than or equal to 6. In interval notation, that's from -3 to 6.